Previously on I don't know what the fuck, but yeah. uh yeah, previously we stopped here. So we stopped at defining our P and Q. This is our so-called the equation um that derive from this equation, the similar to the case 3 equation, I would say. And then let me see. So as promised, next video, I mean this video will derive the unknowns. So the first thing I need you to know is that you have to understand what is the difference between the damping frequency, and the natural frequency. Natural frequency is the natural frequency of the spring. Okay, the very undisturbed system. So it will be like, keep oscillating and oscillating to the end. Okay. When you have a friction, you are talking about damping frequency. Damping frequency, as you can see, is incorporated with the natural frequency in it. So natural frequency affects the damping frequency. Therefore, as you can see, this damping is is dependable on the damping frequency, and therefore we can say that this type of trend, the frequency itself is in terms of damping frequency. Okay, if there's no damping, it keeps oscillating and oscillating until no end. Okay, then it is natural frequency. And therefore, from this, we can actually say that from this graph, this is what we call damping frequency. So we can actually find our actual natural frequency. Okay, the undamped natural frequency means that it is it is it is oscillating. Okay, undamped natural frequency is this dude. If it's a damped one, it's this one. Okay, so where are we? Oh, okay. So WD, the damping frequency, is this, and therefore as you know, frequency is 2 pi over period. So we are given that our initial condition from last video, that one cycle is equal to 3 seconds, right? So therefore, um, our damping frequency is actually 2.094 radian per second. Okay. Take note that when you're multiplying things, right, you have to take 2 times 3.142. Okay, let me change it there, which is this. Okay, 2.094. I mean 2 times 3.142 over 3 seconds. So the next step, right, is to actually find um, the rest of the things, and then one the first thing we need to find is to actually find the damping factor. Okay, the damping ratio, which is this one. Okay, so what we can actually do is to sub in initial condition again, but instead it's our initial condition. Okay, we can actually use the graph, since that we are given the graph itself. So from the graph itself, when the displacement x is equals to 0, the time is equals to 1. So we can exploit this thing to actually help us to find an equation that could solve for our damping factor. So give me a minute. I forgot where I stopped. Ta-da! I think I stopped here. Okay, I think I stopped here. So yeah, from graph, when t is equals to 1 second, okay, I think you already know what I'm saying, because for about past an hour, whatever, okay, whatever. So, so I'm very tired. So from graph, when t is equal to 1 second, um, time is equal to 1 second, our x displacement is 0, right? So from this, we can deduce, and so from this, we can sub in this condition into our parameter over here. If you remember, this comes from the equation of this, right? And then we sub in our P and Q, and then now we sub in our conditions when t is equals to 1 second. So we sub in this is 1, this is 1, this is 1. Okay, and then equals to 0 because everything is equals to x. If you remember, the equation is equals to the displacement x. And so where are we? And so this is it, and then the t becomes 1, so they multiply cosine WD, the same thing. And then after which, we determine which part we set the equation to 0. Okay, our purpose here is actually to find our our purpose here is actually to find our damping factor. Okay, purpose here is to find damping factor. Okay, damping factor. So we already know our WD. Okay, which is this dude over here. So the problem now is only with the damping factor. Once we find this, everything is happy. Why do you say so? Okay, why do I say so? If you can see, WD is equals to Wn1 minus damping factor. Okay, since we know WD, we know, then we need to find damping factor. The rest is like a mao. Okay. Uh, anyway, and then determine which part will set the equation to 0, and therefore there is one part, right? This part and this part. And previously we say that this part is the exponential part and this part is the sinusoidal part. Okay, which is like this. Exponential, sinusoidal, when they add together they become damping. And so the exponential form cannot be towards 0, because if you sub in 0, omega 0 or damping factor is equal to 0, you will never ever get e to the power of 0 is always 1, not 0. So this is impossible to get 0. Thus we can deduce that this is equal to 0. And therefore, we solve for our damping factor. Okay, you may wonder why I left out this one. This is just saying that therefore this is equals to 0, saying that. Okay, so if you have this equation equals to 0, you just rearrange a lot of things. Now we because we didn't input our WD, so now we input our WD inside here, and then you can solve. So you just bring fota 40 cosine 2.094 equals to 40, I mean 40, and then blah blah blah, and then what the fuck am I? Hold on a while. Okay, that's set. Okay, so it's 2.094, and then you just bring, cause previously I was just bringing this one towards here, so it's negative, right? 40 equals to negative, this one bring over. Okay, and then now the tricky part comes in. Okay, this one, okay, will goes up here. Okay, will goes to the, like, I mean here lah, multiply, and then this cosine will comes down. So that's why sine divided by cosine 2.94, and then this one comes up, and this 40 then damping factor will go down, and therefore we have this what do I call, um yeah, this dude over here. And then you may be wondering why is the 40, right? The 40 is actually cancelled. Okay, so therefore 1 minus, it's just switching the sign. This one come out, I mean this one come out, this one come down, so this is just like that. And then I also forget to put in the negative sign. Okay, after which we can bring this damping factor up here, so it will be like after this one is tangent. Okay, if you were to write it down, maybe so this one is tangent 2.094. Okay, so tangent 2.194, make sure you know this is radian. Okay, when this one important key thing is that make sure when you're dealing with evaluating sine cosine values, you make sure you're dealing with radian, because normally when you're dealing with all these things, they are in terms of radian per second, so you have to go with radian. Okay, so if you were to bring this up, you'll be minus 1.734 radian, and then because now you square root, you bring over here is square, so therefore it's this value, and then you rearrange, you eventually get the damping factor is equals to 0.49965. So as I say, once you get your WD, I mean WD and your damping factor, okay, you can find the rest. Okay, so therefore let's find our natural frequency. Okay, the first thing first, because the one that the key to everything is natural frequency. Anyway, so this is WD equals to blah blah blah, and then it's pretty easy now. So typically it's just subbing in. Okay, so Wn so this is the equation, and then we know our Wd, we know our damping factor. I think you work it out lah. You know what is it already. Um, yeah, so this one will come down, then you sub in, and you get this value. And then since after you get your natural frequency, you can find k because you know your mass. Similarly, you just square this, and then you and then you get k and then uh, after which you know your okay. Now this after you know k already, so now let's go back to dealing with the damping factor. The damping factor consists of, if you remember, there is consists of the C, O, and the I mean the the damping coefficient and the critical damping coefficient. Okay, so the critical damping coefficient is actually C naught and is equals to 2m omega natural frequency. Okay, so therefore since we know natural frequency, everything is easy, so we just sub in. Okay, and eventually this is it, 2 times 4000 times omega 2.418, which is we found earlier, I mean 6 8 whatever. Okay, yeah, and you eventually get C naught. So C naught itself is the critical damping factor, and maybe I can give you a follow-up. Considering what is C naught actually critical damping factor. So the critical damping factor coefficient C naught is actually the C naught itself that could cause the system to be just nice to, no oscillation. Okay, so there will be no oscillation. So therefore we are comparing with just nice, there is no oscillation type. Okay, so this is typically applicable for under them, I think. Yeah, I believe. And yeah, so this is the C naught as I said earlier, because C naught is equals to 2m omega natural frequency, and then with this and also the damping factor, you can easily find your damping coefficient C. Okay, the damping coefficient C, which is the damping coefficient of your damper of the original system, of your own system. Okay, so I just want to make clear one thing is that this coefficient is the damping coefficient of your mass. I mean of your damper. Okay, of your system's damper. This one is when your system is um without damper. Okay, if your system is without damper, is this one. Okay, so just comparing like somewhat the efficiency. No, okay, don't, okay, just say comparing. Okay, that's all. Then you can see. And then now we have successfully found out our actual and undamped natural frequency. We know our spring stimulus K. We know critical and actual natural damping coefficient. We are cool. And just to summarize, what we have done for this question. Okay, so you can have a total full concept of what the fuck we are doing. Um, the first thing we need to do is to actually define all the given parameters. This is what a lot of questions. If you see a graph, typically you will have to do that. Okay, you see a graph, you do that, you find all your typically you have to figure out all the amplitudes, your period, your cycles, your time, the cycle, and everything. So it's all on the initial condition, and then after which you write down all equations that relate to your questions that the questions want you to find. And then after which you observe the trend of the graph, see whether is it under them, over them, or whatever them, and then you get whatever equation that corresponds to that. And then you solve for your particular, your particular solution, P and Q. Make sure that by subbing in your initial condition, then you solve your P and Q, and you derive an equation. And then after that, in this video, we actually try to solve, since we already know our equation, because if this equation, then you can actually solve fully for the WD natural frequency, and actually with this you can actually straight away solve for your natural frequency and the damping factor. WD is, as I said earlier, is this one. Okay, when you have damper is damper frequency. When you have no damper is natural frequency, and therefore from this concept, you will know that WD is equals to this relationship, and then now you need to find the actual frequency and also the damping factor. So the first thing I need to find is to find the damping factor first. Okay, so damping factor first, you use the same equation. You set up whatever initial condition using a graph, and then you do, and then you get a damping factor. Once you get a damping factor, everything is easy, and then you get it. And so I hope I make everything pretty clear. Although, yeah, I'm very tired. I started from morning 9 o'clock until now 5 afternoon. I'm very proud of myself. Last time I used to play from 9 o'clock to 5 o'clock, or even 12 hours. But now, yeah. Okay, so next video I'll just do a summary of the whole lesson 3, and then I'll just call it a day. Bye bye.